There is a light in the darkness tonight, not the light of distant suns burning hydrogen into helium across millions of years, not the reflected glory of planets orbiting their parent stars. This light is different. This light is green. And this light should not exist. If you're enjoying what we're discovering here, don't forget to hit that like button and subscribe to the channel. Your support helps us keep bringing you fascinating facts about the Three-Eye Atlas as they unfold in real time. And I'd love to know. Where are you watching from? And what time is it there? Drop your answer in the comments below. On July 1st, 2025, a telescope in Chile noticed something moving. The Asteroid Terrestrial Impact Last Alert System, ATLAS for short, is designed to find rocks that might threaten Earth, but what it found that night threatened nothing except our understanding of what's possible. The object was designated C/2025N1, but astronomers gave it another name, a simpler name that tells you everything you need to know about how extraordinary this visitor is, 3I/Atlas. The 3I means it's the third confirmed interstellar object ever detected entering our solar system. Not from the scattered debris of our own sun's formation, not from the distant Oort cloud that still orbits, however loosely, the star that made us. This object formed around a different star, under different conditions, perhaps billions of years before our own Earth existed, and then, for reasons we're still trying to understand, it was cast out, ejected, sent wandering through the lightless spaces between the stars. How long did it wander? We can only estimate. The preliminary calculations suggest this object may be 3 billion years old, perhaps as old as 11 billion years. Our solar system, our sun, our Earth, everything we've ever known, is only 4.6 billion years old. This visitor is older than our world. But that's not why we're here tonight. Age alone doesn't make something impossible. The universe is filled with ancient things. What makes 3I Atlas impossible is simpler, more immediate, more challenging to everything we thought we understood about how matter behaves in the cold of space. 3I Atlas is glowing with nickel vapor, and it's doing it where nickel vapor cannot exist. Let me be clear about what that means. We're not talking about solid nickel embedded in rock and ice. Every comet, every asteroid, every planetary body contains metals. Iron, nickel, magnesium, the products of supernovae, baked into the ingredients of planets and smaller objects when star systems form. That's normal, that's expected. What's not expected is vapor. Gas. Individual nickel atoms floating freely in space, excited by ultraviolet light, emitting their characteristic green glow at 5,867 angstroms. Because nickel doesn't do that, not this far from the sun, not at these temperatures. To turn solid nickel into vapor, you need heat, significant heat. The sublimation temperature of nickel, the point at which it transforms directly from solid to gas, is roughly 1,400 degrees Celsius. At 3I Atlas's distance from the sun when these observations were made, the surface temperature of an object would be somewhere around negative 140 degrees Celsius. That's a difference of more than 1,500 degrees, and yet the nickel is there, glowing, undeniable, captured in spectrum after spectrum by multiple observatories. The European Southern Observatory's Very Large Telescope detected it. Other instruments confirmed it. This isn't an error. This isn't noise in the data. This is real. This is impossible. Piali Rahat-Gonka, working with colleagues at the University of Canterbury in New Zealand, was among the first to analyse what they were seeing. When you spend your career studying the spectroscopic signatures of comets, you learn what to expect. You learn the patterns, water sublimating as sunlight warms the ice, carbon dioxide outgassing, cyanide radicals, sodium, sometimes calcium, but nickel, this far out. The team published their findings, and the title of the paper captured the strangeness perfectly. Detection of nickel emission in the interstellar comet 3I/Atlas at heliocentric distances too large for thermal sublimation, too large, too cold, too impossible, and yet, here's what makes it even stranger. When we detect metal emission from comets, and yes, we do occasionally see it, but much closer to the sun where temperatures allow it, we typically see iron and nickel together. They're cosmic companions, They form together in the nuclear furnaces of dying stars. They travel together in the debris clouds that become new star systems. They embed together in the planetesimals and comets that form from those clouds. Iron and nickel, always together. The ratio varies depending on the conditions under which they formed, but they appear together. It's one of the constants of cosmic chemistry. But 3I Atlas is showing us nickel without iron, strong nickel emission, clear, unmistakable, and no corresponding iron signature. The iron should be there. If conditions exist that can vaporize nickel, they can vaporize iron. Iron's sublimation temperature is actually slightly lower than nickel's. If anything, we should see more iron than nickel, but we don't. We see nickel, just nickel. Now, before we go further, I want you to understand something. This documentary is going to take you deep into the science of what we're observing. We're going to explore the chemistry, the physics, the observational techniques. We're going to look at competing hypotheses and untested theories. We're going to venture carefully into speculation about what this might mean. But underlying everything, supporting every question we ask, every possibility we explore, is this foundation of impossibility. We're seeing something that should not be happening. And when the universe shows you something impossible, you have two choices. Either your understanding of what's possible is incomplete, or you're witnessing something genuinely new, something that will require you to expand the boundaries of known science. 3I Atlas is offering us that choice. This isn't the first time. Astronomy has always been a science of impossible things that turned out to be real. Galileo's moons of Jupiter, impossible because everything was supposed to orbit Earth. Uranus, impossible because there were only 6 planets and everyone knew it. Pulsars, impossible because no known physics could make a star flash with millisecond precision. Each time the impossible became the mundane, not because the phenomenon changed, but because our understanding expanded to include it. So what we're doing tonight, what we're going to spend the next 2 hours doing, is sitting with this impossibility, turning it over, examining it from every angle, asking not, how do we dismiss this? But, what is this trying to teach us? Because 3I Atlas didn't come here to confuse us. It's not trying to be mysterious, it's simply being what it is. An object from another star system, carrying with it the chemical signature of conditions we've never directly observed. Conditions that existed in a stellar nursery that died or dispersed before humans existed, before dinosaurs existed, possibly before complex life arose on Earth at all. This object is a messenger, not an intelligent message. We have no evidence of that, and we'll address that question carefully later in this documentary, but a message nonetheless. Information, data, evidence from a place we cannot visit, from a time we cannot return to, about processes we've only theorized about, and the first word of that message is written in nickel vapor, glowing green in the darkness, 3.88 astronomical units from our sun. 3.88 astronomical units. Let me put that in perspective. 1 astronomical unit is the distance from Earth to the Sun, roughly 93 million miles. 3.88 AU means 3I Atlas was about 360 million miles from the Sun when this nickel emission was first detected. That's roughly the distance of the asteroid belt, well beyond Mars, in the realm where sunlight is weak and temperatures plummet, and there, in that cold and distant place, nickel was vaporizing. The question that will drive this entire documentary, the question that will take us through chemistry and physics, through speculation and wonder, through what we know and what we can only imagine, is simply this. How? How is the nickel vaporizing? What energy source is powering this transformation? What does it tell us about where this object came from, what it's made of, how it formed? And perhaps most intriguingly, what does it tell us about the possibilities we haven't yet considered? Those are the questions we're here to explore. So let me tell you what we're going to do. In the next section, we're going to become spectroscopists. We're going to learn how we detect elements in space, how we know with certainty that what we're seeing is nickel, and why the specific wavelengths matter. We're going to understand the tool that revealed this mystery before we try to solve it. Then we'll dive deep into the chemistry. What is nickel? Where does it come from? How does it behave? What are the known mechanisms that can vaporize it? And why don't those mechanisms explain what we're seeing? After that, we'll explore hypotheses, solar-wind interactions, exotic composition, subsurface heat. Every scientific explanation that's been proposed, we'll examine carefully and honestly. And then, only then after we've done the science, we'll venture into the more speculative territory, the questions that don't have answers yet, the possibilities that push at the edges of what we know, but we'll do it responsibly. We'll do it with respect for the scientific method and the evidence. Because the truth is strange enough without embellishment. The universe is mysterious enough without invention. Three-Eye Atlas is teaching us something. Our job is to listen. Before we move on, I want you to feel the magnitude of what's happening right now. As I speak these words, as you hear them, Three-Eye Atlas is out there, moving, travelling at roughly 62 kilometers per second relative to our Sun. It passed its closest approach to the Sun in late October 2025. It's now heading outward, accelerating as the Sun's gravity releases its grip. On December 19th, 2025, it will make its closest approach to Earth. 1.8 astronomical units. Still distant, nothing to fear, but close enough for detailed observations, close enough for every major telescope on Earth and in space to turn its attention to this visitor, and then it will leave, forever. Its trajectory is hyperbolic. Eccentricity of 6.137. Those numbers mean it's not bound to our Sun. It's travelling too fast for gravity to hold it. When it leaves, it will never return. In January 2026, it will pass beyond the orbits of the outer planets, accelerating into the darkness, heading toward another part of the galaxy entirely. We have weeks, maybe a few months if we're lucky and the observing conditions hold, and then this opportunity, this chance to study an object from another star system up close, will be gone. That's why this documentary series exists. That's why we're taking the time to really understand what we're seeing. Because opportunities like this are vanishingly rare in a human lifetime. The first interstellar visitor we detected was Oumuamua in 2017. Strange, elongated, accelerating in ways we still debate. Then came 2I/Borisov in 2019. A comet that looked like our own comets, reassuringly normal after the weirdness of Oumuamua, and now Three-Eye Atlas, active, unusual, vaporizing nickel where nickel shouldn't vaporize, 3 visitors in 8 years. We don't know if that's typical or if we're living in a special time. We don't know if there are thousands of these objects passing through our solar system at any given moment, invisible until we get lucky, or if they're genuinely rare. What we know is that this one is here, now, glowing green with impossible nickel vapor, carrying secrets from another star. And we have a choice. We can shrug and say, that's weird, and move on. Or we can do what humans do best. We can ask why, we can investigate, we can wonder. This is the story of the nickel enigma, the impossible emission, the green light in the darkness that shouldn't exist. This is the story of what Three-Eye Atlas is teaching us about the universe beyond our Sun. This is a story about chemistry and physics and observation and wonder, about what we know and what we're learning, and what we may never fully understand. But most of all, this is a story about paying attention, about noticing, about taking the time to really see what the universe is showing us. Because that green glow, that impossible nickel vapor, it's telling us something. Something important, something we've never heard before, and for the next 2 hours we're going to listen. Let's talk about how we know it's nickel. Before we can understand what makes the nickel emission from Three-Eye Atlas impossible, we need to understand how we know it's nickel in the first place. How can we possibly identify a specific element in an object hundreds of millions of miles away? How can astronomers be certain, not guessing, not estimating, but certain, that what they're detecting is nickel and not something else? The answer is spectroscopy, and it's one of the most powerful tools humans have ever developed for understanding the universe. The story begins with Isaac Newton in 1666. Newton took a prism, a triangular piece of glass, and let sunlight pass through it. The white light separated into colours: red, orange, yellow, green, blue, violet. A rainbow. Newton called it a spectrum. At the time, this was considered a property of the prism. People thought the glass was somehow adding colour to the white light, but Newton proved otherwise. He took the separated colours and recombined them with a second prism, producing white light again. The colours weren't being created, they were already there, hidden in the white light, and the prism was simply spreading them out. This was revolutionary. But the real revolution came later. In the 1800s, scientists developed more sophisticated instruments, spectroscopes. These devices didn't just split light into colours, they split it with precision, allowing observers to see not just a smooth rainbow, but something far more interesting. Dark lines. Thin, precise black lines crossing through the spectrum at specific wavelengths. When they looked at the sun's spectrum, they saw hundreds of these lines. When they looked at other stars, they saw different patterns of lines. When they heated different elements in the laboratory and looked at the light they emitted, each element produced its own unique pattern. Sodium produced two bright yellow lines close together. Hydrogen produced a red line, a blue-green line, a violet line. Iron produced a forest of lines. Every element had its own signature, its own fingerprint written in light. This discovery changed everything. Suddenly, we could identify what distant objects were made of without ever touching them. We could analyse the composition of the sun, of stars light years away, of nebulae and galaxies, and eventually comets. Because here's the beautiful thing about atoms. They don't lie. An atom of nickel anywhere in the universe will produce the exact same spectral lines as an atom of nickel in a laboratory on Earth. The wavelengths are determined by the energy levels of the electrons orbiting the nucleus. Those energy levels are set by the fundamental forces of nature. They don't change based on location or time. A nickel atom forged in a supernova 10 billion years ago, incorporated into a comet in a star system hundreds of light years away, vaporizing in the outer solar system today, it will still produce the exact same spectral signature, 5,867 angstroms. That's the wavelength of one of nickel's brightest emission lines. It's in the green part of the visible spectrum. When nickel atoms are excited by ultraviolet radiation, when their electrons jump to higher energy levels and then fall back down, they emit photons at this precise wavelength. And that's what multiple observatories detected coming from 3I Atlas. Let me show you what the data looks like. This is a spectrum taken by the European Southern Observatory's Very Large Telescope. The horizontal axis represents wavelength, different colours of light. The vertical axis represents intensity, how much light at each wavelength. Most of it is a relatively smooth curve. The comet is reflecting sunlight, which produces a continuous spectrum. But there, right there, you see that spike? That sharp peak at 5,867 angstroms? And that's nickel, not probably nickel, not something that looks like nickel, that is nickel. The wavelength matches perfectly. The line width matches what we'd expect from atoms in a gas at these temperatures. The intensity tells us roughly how much nickel vapor is present. And here's what makes this detection so powerful. There's nothing else that can produce that signature. No other element, no other molecule, no instrument artifact or observational error produces a bright emission line at exactly 5,867 angstroms. When you see that line in a spectrum, you're seeing nickel. Period. This is why astronomers can be so certain about what they're observing. Unlike images, which can be ambiguous, is that a rock or ice? Is that feature natural or unusual? Spectra are unambiguous. They're quantitative. They're precise. If you detect the hydrogen alpha line at 6,563 angstroms, you're seeing hydrogen. If you detect the sodium D lines at 5,890 angstroms, you're seeing sodium. If you detect the nickel line at 5,867 angstroms, you're seeing nickel. It's not interpretation, it's identification. And the observations of 3I Atlas weren't a one-time thing. The nickel emission was detected on multiple nights, by multiple instruments, by multiple independent teams of astronomers. This wasn't a fluke, this wasn't noise, this was a consistent, repeatable signal. Piali Rahat-Gonca's team observed it. Thomas Puzia at Pontificia Universidad Católica de Chile observed it. As the data was shared and verified, the conclusion became inescapable. 3I Atlas is emitting nickel vapor. But here's where the impossibility begins to crystallize, because we don't just see the nickel emission, we can measure it, we can quantify it, and when we do, the numbers make no sense. The amount of nickel vapor being emitted, the brightness of that emission line, is substantial. This isn't a trace amount, this isn't a barely detectable whisper, this is a clear, strong signal. The nickel to cyanide ratio is orders of magnitude higher than what we see in typical solar system comets. Orders of magnitude. That means not just a little more, that means tens or hundreds of times more nickel relative to other species we'd expect to see. And it's happening at 3.88 astronomical units from the Sun, where the solar flux, the amount of sunlight hitting the comet's surface, is only about 7% of what Earth receives. The surface temperature at that distance would be somewhere around negative 140 degrees Celsius. At that temperature, nickel is a solid that requires temperatures above 1,400 degrees Celsius to sublimate into vapour. So how is the nickel vaporising? That's the question. That's the enigma. Now, I want to address something before we go further. Some of you might be thinking, maybe it's not actually vaporising, maybe there's some other process. And that's good scientific thinking. We should always question our assumptions. But here's the thing, the spectral emission we're seeing requires vaporised nickel. Solid nickel doesn't emit light at 5,867 angstroms. Nickel embedded in rock or ice doesn't emit at that wavelength. You need free nickel atoms, individual atoms in a gaseous state, for this emission to occur. The atoms need to be excited by ultraviolet radiation, which means they need to be exposed to sunlight, not buried in the interior, and when they de-excite, they emit the photon we detect. This is basic atomic physics. There's no ambiguity here. To produce the emission we're seeing, nickel must be in vapor form, not liquid, not solid, not bound in molecules, individual neutral nickel atoms in a gaseous state, which means somehow, despite the cold, despite the distance from the Sun, despite everything we know about sublimation temperatures, the nickel is vaporizing. So now we have our mystery fully defined. We know with certainty that nickel vapor is present. We know it shouldn't be possible through normal thermal sublimation. We know it's happening anyway. The next section is going to dive deep into the chemistry and physics of what we're observing. We're going to explore nickel itself, where it comes from, what it is, how it behaves. We're going to look at sublimation physics in detail, and then we're going to examine every hypothesis that's been proposed to explain this impossible observation. Some of those hypotheses are exotic but scientifically grounded. Others push at the boundaries of known physics. A few venture into territory that makes scientists uncomfortable, but we'll address them anyway, because intellectual honesty requires us to consider all possibilities. But here's what we're not going to do. We're not going to dismiss the impossibility. We're not going to wave our hands and say, well, obviously there's some explanation, without actually working through what that explanation might be. Because the truth is, as of right now, as of November 2025, we don't have a complete explanation. We have hypotheses, we have possibilities, we have ideas that need testing, but we don't have an answer, and that's okay. That's how science works. The universe shows us something unexpected. We observe it carefully, we measure it precisely. We rule out explanations that don't fit the data, and gradually, through careful thought and continued observation, we narrow down the possibilities until we find the truth. 3i Atlas is at the observe it carefully stage. We're gathering data, we're measuring, we're thinking. And what we're discovering is that this object is stranger than we first realized. The nickel emission isn't the only unusual thing about 3i Atlas. As we'll see in later sections, this comet is challenging our understanding in multiple ways. The nickel is just the most dramatic, the most impossible. The thing that grabs your attention and says, look at me, something strange is happening here. But beneath that surface strangeness, there are deeper mysteries. Questions about composition and formation. Questions about how long this object has been wandering the galaxy. Questions about what conditions existed in the star system where it formed. And those questions matter, because 3i Atlas isn't just one weird comet, it's a data point. One observation in our growing catalogue of interstellar objects, and as we collect more of these data points, as we detect more visitors from other star systems, patterns will emerge. Maybe the nickel emission isn't unique to 3i Atlas. Maybe it's characteristic of objects from a certain type of star system. Maybe it tells us about the chemistry of planet formation in environments very different from our own. Or maybe, and this is the possibility that keeps astronomers up at night, maybe it's telling us that our understanding of how comets behave is incomplete. Maybe there are processes we haven't accounted for, energy sources we haven't considered, mechanisms we haven't discovered. The beauty of the scientific method is that it makes space for these possibilities. We don't have to choose an explanation and defend it. We can hold multiple hypotheses simultaneously, testing each against new data as it becomes available, And right now, with 3I Atlas still observable, still glowing green with its impossible nickel vapor, we're in the data collection phase. We're watching, we're measuring, we're learning. Let me paint you a picture of what's happening right now as I speak these words. Somewhere on Earth, a telescope is probably pointed at 3I Atlas. Maybe it's the Very Large Telescope in Chile. Maybe it's Hubble, in orbit above the atmosphere. Maybe it's one of the dozens of observatories that have requested time to observe this object. A spectrograph is collecting photons. Light that left 3I Atlas minutes ago is arriving at a detector, being spread into a spectrum, being recorded digitally. Later, maybe in a few hours, maybe tomorrow, an astronomer will look at that spectrum. They'll see the nickel line. They'll measure its intensity. They'll compare it to observations from previous nights. Has it changed? Is the emission getting stronger as the comet moves farther from the sun? Weaker, staying constant? Each data point is a clue. Each observation constrains the possibilities. This is how we solve cosmic mysteries. Not with sudden revelations or eureka moments, though those happen occasionally, but with patient, careful, systematic observation and analysis. And you're part of it. By watching this documentary, by learning about what we're seeing, by caring about these questions, you're participating in this moment of discovery. You're one of the humans who looked up at the sky and wondered what that green light means. Now, let's get technical. Let's dive into the chemistry and physics of what we're observing. Let's understand nickel, truly understand it, so we can appreciate just how strange it is to find it vaporizing in the outer solar system. Are you ready? Good. Let's talk about where nickel comes from. Every nickel atom in 3I Atlas was forged in a star. Not just any star, a massive star. A star that lived fast and died violently in one of the universe's most energetic events. A supernova. To understand why nickel vaporizing is so strange, we need to understand what nickel is. Not just chemically, element number 28 on the periodic table, but cosmically. Where does it come from? How is it made? Why does it exist at all? The answer takes us to the hearts of dying stars. When the universe began, in that first fraction of a second after the Big Bang, only the simplest elements existed. Hydrogen, helium, traces of lithium. That's it. Everything else, carbon, oxygen, nitrogen, iron, nickel, gold, uranium, all of it had to be made later. Made in stars. Stars are fusion reactors. In their cores, extreme temperatures and pressures force atomic nuclei to merge, creating heavier elements. Our sun, for example, is fusing hydrogen into helium. 4 hydrogen nuclei combine to make one helium nucleus, releasing energy in the process. That's what makes the sun shine. But the sun will never make nickel. It's not massive enough. When it runs out of hydrogen in its core, it'll fuse helium into carbon and oxygen for a while, and then it'll die, shedding its outer layers as a planetary nebula, leaving behind a white dwarf. To make nickel, you need a more massive star. You need a star with at least 8 times the sun's mass, maybe 10 or 20 times, a star that lives fast and burns through its nuclear fuel in millions of years instead of billions. When a massive star exhausts the hydrogen in its core, it doesn't die, it contracts. The contraction raises the temperature until helium can fuse into carbon. Then carbon fuses into neon, neon fuses into oxygen, oxygen fuses into silicon. Each stage produces heavier elements. Each stage releases energy that holds the star up against gravity's crush. Each stage happens faster than the one before. Hydrogen fusion lasts millions of years. Helium fusion, hundreds of thousands. Carbon, thousands. Silicon fusion, the final stage, lasts about 1 day. 1 day, and at the end of that day, the core of the star is made of iron and nickel, the most stable nuclei in the universe, the endpoint of fusion, and then fusion stops. Because you can't fuse iron or nickel and release energy. Fusing them requires energy. They're at the bottom of the energy curve, the most stable configuration, so the energy generation stops, and without energy pushing outward, gravity wins. The core collapses. In less than a second, a core the size of Earth collapses to a sphere 20 kilometers across. The density becomes so extreme that protons and electrons are crushed together into neutrons. A neutron star is born. And the collapse releases so much energy, so much gravitational potential energy, converted to kinetic energy, that the outer layers of the star explode. The explosion is called a supernova. For a few weeks, A single dying star can outshine an entire galaxy. In that explosion, something miraculous happens. The intense flux of neutrons, free neutrons released by the collapsing core, bombards the iron and nickel in the star's outer layers. Neutron capture occurs. Radioactive isotopes form. Some of them decay, converting neutrons to protons, creating elements heavier than iron. Gold, platinum, uranium. This is where the heaviest elements come from. Not from stellar fusion, but from the neutron flux of a supernova. And the nickel? Some of it was already there, produced in the silicon fusion stage. Some of it was created in the neutron bombardment. All of it, along with iron, cobalt, and the other products of a massive star's life, is ejected into space at thousands of kilometers per second. The debris spreads, it cools, it mixes with interstellar gas, and eventually, millions or billions of years later, it becomes part of a new nebula, a stellar nursery where new stars and planets and comets form. This is where 3I Atlas's nickel came from. Not from our sun, not from our solar system's formation, from a supernova that exploded billions of years ago in a part of the galaxy we can't identify, around a star we'll never see. The nickel in 3I Atlas is supernova ash, ancient metal, the product of nuclear fusion and violent death. And now, billions of years later, that metal is vaporizing in our outer solar system. Atoms that were forged in temperatures of billions of degrees that have been frozen solid for eons are becoming gas again. How? Let's talk about sublimation, the process by which a solid becomes a gas without passing through a liquid phase. This is what happens when dry ice, solid carbon dioxide, evaporates at room temperature. It doesn't melt into liquid CO2. It goes directly from solid to gas. Comets work the same way. As they approach the sun, the ice on their surface heats up. When it gets warm enough, the ice sublimates. Water ice, carbon dioxide ice, methane ice, they all turn to gas. That gas escapes, carrying dust with it, forming the coma and tail that make comets visible. But sublimation requires energy. You have to break the bonds holding the solid together. For water ice, that happens at around -100 degrees Celsius in the vacuum of space. For carbon dioxide, it happens at much colder temperatures, around -130 degrees. For nickel, it requires temperatures above 1,400 degrees Celsius. 1,400 degrees. Let me give you some perspective on that temperature. Steel melts at around 1,370 degrees. Lava from a volcano is typically between 700 and 1,200 degrees. The surface of Venus, the hottest planet in our solar system, is about 470 degrees. Nickel doesn't sublimate easily. It really doesn't want to become a gas. You have to force it with extreme heat, and 3I Atlas, at 3.88 AU from the Sun, is nowhere near that hot. The sunlight at that distance is weak. The surface temperature of the comet would be somewhere around -140 degrees Celsius, cold enough that even water ice would barely be sublimating. Yet the nickel is there, vaporizing, emitting light. Some of you might be thinking, well, maybe there's a hot spot. Maybe there's concentrated sunlight. Maybe the surface isn't uniformly cold, and that's reasonable thinking. Comets aren't perfect black bodies. They have irregular shapes, they rotate. Some areas might face the sun more directly than others. Maybe there's a cliff or a crater that concentrates heat. But here's the problem. We're not talking about a small temperature increase. We're not talking about making the surface 50 degrees warmer. We need to increase the temperature by 1,500 degrees. That's not a hotspot. That's a fundamentally different energy source. Let's go through the possibilities systematically. What could generate that much heat in the outer solar system? This is how normal sublimation works. Sunlight hits the surface. The surface absorbs the energy. The temperature rises until there's equilibrium between incoming energy and energy radiated away as infrared. At 3.88 AU, this gets you to maybe -140 degrees Celsius, nowhere near enough for nickel. Option 2. Subsurface heating. Maybe the surface is cold, but there's heat trapped below. Perhaps radioactive decay of long-lived isotopes, aluminum-26, potassium-40, is generating warmth in the interior. This actually happens in some bodies. Earth's interior is warm partly because of radioactive decay. But the amount of radioactive material would have to be extreme to generate the temperatures needed for nickel sublimation. And if the interior was that hot, we'd see other evidence. The comet would be outgassing prodigiously. We'd see massive activity, water vapour, carbon dioxide, complex organics, everything would be sublimating. We don't see that. 3I Atlas is active, yes, but not exceptionally so. The nickel emission is strong relative to other species, but the overall outgassing isn't consistent with an interior heated to 1,400 degrees. The solar wind, the stream of charged particles flowing from the sun, can impact a comet's surface and knock atoms free. This is called sputtering. You don't need sublimation temperatures. The kinetic energy of the impacting particles does the work. This is actually a real mechanism. We've detected sputtered atoms from other comets. Sodium and calcium particularly can be released this way, but nickel is heavy. Much heavier than sodium or calcium. To sputter nickel efficiently, you'd need much more energetic impacts. And the amount of nickel we're seeing, the brightness of that emission line, suggests a lot of nickel is being released, more than sputtering alone would easily explain. Plus, sputtering has another signature. The sputtered atoms have high velocities. They're kicked off the surface violently. We can measure the Doppler broadening of spectral lines to see how fast atoms are moving. If the nickel was primarily sputtered, we'd expect to see very broad lines. We don't. The nickel emission line has the width consistent with thermal velocities at normal sublimation temperatures. The atoms aren't moving unusually fast. They're acting like they've been gently sublimated, not violently ejected. Here's where things get interesting. Maybe the problem isn't the temperature. Maybe it's our assumption about what form the nickel is in. We've been assuming the nickel is in pure metallic form, or at least in a metallic matrix like it is in iron nickel, alloys, and metallic nickel does require those extreme temperatures to sublimate. But what if the nickel in 3I Atlas is in a different form? What if it's bound in molecules or compounds that sublimate more easily? This is actually scientifically plausible. We know of nickel compounds that are more volatile than pure nickel. Nickel carbonyl NiCO4 is a gas at room temperature. It's toxic as hell, which is why industrial chemists treat it with great respect. But it exists. It's volatile. Could 3I Atlas contain nickel carbonyl, or some other volatile nickel compound we haven't considered? The challenge with this hypothesis is the spectroscopy. The emission we're seeing is from neutral nickel atoms, Ni in spectroscopic notation. Not nickel ions, not nickel bound in molecules, free neutral atoms. If nickel carbonyl was sublimating, we'd expect to see molecular bands in the spectrum, the characteristic signatures of molecules rotating and vibrating. We'd also see carbon monoxide emission, since breaking up NiCO4 would release CO. We see neither. We see clean atomic nickel emission, which suggests that by the time the nickel is emitting light, it's no longer bound in molecules. But, and this is important, that doesn't rule out the possibility that it started as a volatile compound. Maybe nickel carbonyl sublimates easily at cold temperatures. Then, when it reaches the surface and is exposed to UV radiation, the molecules break apart. The CO drifts away. The nickel atoms remain, get excited by UV, and emit at 5,867 angstroms. This is actually one of the leading hypotheses. Not proven, but plausible. It fits the observations without requiring impossible temperatures. If 3I Atlas does contain volatile nickel compounds, that tells us something profound about where it formed. These compounds don't form easily. They require specific conditions: cold temperatures, carbon monoxide-rich environments, low oxygen content, because oxygen would preferentially bind with the nickel to form nickel oxide, which isn't volatile. These conditions might exist in certain protoplanetary disks, young star systems where the chemistry is different from what produced our solar system. Maybe the star was more carbon-rich. Maybe the disk was metal-rich due to proximity to recent supernovae. Maybe the formation happened in a denser part of the interstellar medium. We don't know. But the nickel emission is giving us a clue. It's telling us that 3I Atlas formed under conditions that allowed volatile metal compounds to be incorporated into cometary ice. That's unusual. That's not what we see in solar system comets, and that's exactly what you'd hope to learn from an interstellar visitor. Chemistry from a different star system, evidence of different formation conditions, a window into the diversity of planet formation processes in our galaxy. Now let me address the other mystery I mentioned earlier, the one that makes this even stranger. Where's the iron? Iron and nickel are cosmic siblings. They're produced together in massive stars. They're ejected together in supernovae. They condense together when new star systems form. In our solar system, iron and nickel appear in roughly a 10-to-1 ratio in most primitive materials. When we see metal emission from comets, on the rare occasions when comets get close enough to the sun for metals to vaporize, we see iron and nickel together. Always. The ratio varies, but they're both there. 3I Atlas shows a strong nickel emission and no corresponding iron emission. No iron atoms emitting at their characteristic wavelengths. No iron ions. Just nickel. This is deeply strange. Iron sublimates more easily than nickel. Its sublimation temperature is slightly lower. If conditions exist that can vaporize nickel, those same conditions should absolutely vaporize iron. We should see even more iron than nickel, but we don't. We see nickel, just nickel. There are a few possible explanations, and none of them are simple. Maybe the volatile compound hypothesis explains this too. Maybe 3I Atlas contains volatile nickel compounds, but the iron is locked up in non-volatile forms. Nickel carbonyl, but iron oxide, or iron sulfide, or iron bound in silicates. This would require very specific chemistry during formation. You'd need conditions that separated iron and nickel, that bound them in different compounds with radically different volatilities. It's possible. Chemistry can be surprisingly specific. But it would be unusual. It would require explanation. Maybe there used to be iron vapor, but it's been depleted. Perhaps 3I Atlas has been outgassing for a long time, since well before we discovered it. The iron, being slightly more volatile, sublimated preferentially. The surface layer became depleted in iron-bearing materials, leaving nickel-rich materials behind. This could work. We know 3I Atlas was showing cometary activity as early as May 2025, when it was 6.4 AU from the Sun. That's very far out for cometary activity. If it's been outgassing for months, differential depletion could have occurred, but you'd still expect to see some iron. Complete absence is hard to explain this way. Maybe 3I Atlas simply formed with an unusual iron-to-nickel ratio. Maybe the material it's made from was enriched in nickel relative to iron. This would be genuinely exotic. It would tell us something remarkable about nucleus synthesis in the star system where 3I Atlas formed. Perhaps that system was enriched by a specific type of supernova. Perhaps it formed from material that had been processed through previous generations of stars in unusual ways. Or, and this is the explanation that makes some scientists uncomfortable, perhaps the nickel was concentrated intentionally. Perhaps we're not looking at natural chemistry at all. We'll address that possibility in detail in Act 3. 4. Now let's stay in the realm of conventional astrophysics and chemistry. The absence of iron is a clue, a significant clue. Combined with the strong nickel emission, the CO2-dominated composition, the unexpected activity level, and the other anomalies we'll discuss later. 3I Atlas is showing us a picture of an object that doesn't quite fit our models. Not wildly different. Not impossible to explain with natural processes, but unusual enough to demand attention. Strange enough to tell us our understanding is incomplete, and that's good. That's how science progresses. The universe shows us something that doesn't quite fit the models, and we're forced to refine the models, to expand our understanding, to consider possibilities we hadn't thought of before. Over the next several months, as observations continue, we'll learn more. We'll get more detailed spectra. We'll watch how the emission changes as 3I Atlas moves farther from the Sun. We'll analyse the data with increasingly sophisticated models. Maybe we'll detect other metal species we've missed so far. Maybe the iron is there, but at wavelengths we haven't checked carefully. Maybe there are other elements, cobalt, chromium, manganese, that will fill in the picture, or maybe the strangeness will deepen. Maybe we'll find more anomalies, more evidence that 3I Atlas truly is chemically distinct from solar system comets. Either way, we're learning. Every photon we collect teaches us something. Let me take a moment to acknowledge the humans doing this work, the astronomers who requested telescope time, the engineers who keep the observatories running, the spectroscopists who calibrate the instruments and reduce the data, the theorists who build models to explain what we're seeing. This is collaborative science at its finest. Teams spread across multiple continents, sharing data, checking each other's work, building on each other's insights. No single person understands 3I Atlas, but collectively, incrementally, we're assembling the picture, and you're part of that collective effort. Not directly, you're not analysing spectra or building models, but culturally. By caring about these questions, by wanting to understand, by investing 2 hours of your life to really think about what this green light in the darkness means. Science doesn't happen in isolation. It happens in a society that values curiosity and evidence and careful thinking. A society that looks at impossible nickel vapor and says, let's figure out why, instead of shrugging and moving on. So thank you for being here, for paying attention, for joining this investigation. Now, we've covered the spectroscopy, how we know it's nickel. We've covered the chemistry, where nickel comes from and why it shouldn't be vaporizing. We've explored several hypotheses: solar wind, exotic composition, volatile compounds. But there's one hypothesis we haven't addressed yet, one possibility that keeps appearing in discussions in papers, in the careful qualification scientists add when they present their findings. What if 3I Atlas isn't entirely natural? What if the nickel emission is evidence of something else, something technological? This is the question Avi Loeb raised, and it's the question we need to address seriously, scientifically, without sensationalism. So let's do that. Let's talk about the technological hypothesis. But before we do, I want to make something very clear. This documentary is committed to intellectual honesty. We're not going to dismiss the question as ridiculous. We're also not going to inflate it into something it isn't. We're going to examine it the same way we've examined every other hypothesis, carefully, critically, following the evidence wherever it leads. Because here's the truth. The universe doesn't care about our comfort. It doesn't present itself in ways that are easy for us to categorize. Sometimes the most natural-sounding explanation turns out to be wrong. Sometimes the weird explanation turns out to be right. Our job isn't to defend what we want to be true. Our job is to figure out what actually is true. But it's plausible, it's consistent with the observations, and it makes predictions we can test with continued observation. If this model is correct, we should see the nickel emission decrease as 3I Atlas moves farther from the sun and the surface cools. The volatile compounds will stop sublimating. If we see that decrease, if the emission shuts off at predictable distances, that supports the volatile compound hypothesis. If instead the emission continues or even increases as the comet moves outward, that would be strange. That would suggest an internal energy source, something generating heat that doesn't depend on solar distance, and that would demand explanation. This is why continued observation is crucial. This is why astronomers are requesting telescope time, pointing everything from ground-based instruments to Hubble to Webb at this object. Each data point constrains the models. Each spectrum teaches us something. We're watching 3I Atlas's nickel emission in real time, as it happens, and in a few months we'll have a time series, a record of how the emission changed with solar distance and time. That data will be invaluable. It will let us distinguish between a volatility-driven emission, which should correlate with solar heating, and something else, which wouldn't. It will let us see if there are variations, outbursts, decreases, changes in the emission profile that tell us about the comet's rotation or surface features. It will give us enough information to build detailed models, to test hypotheses, to rule things out. This is the scientific method in action. Observe something strange, develop hypotheses to explain it, make predictions based on those hypotheses, collect more data, see which hypotheses survive. It's not dramatic. There's no eureka moment, just careful, systematic work. But it's powerful. It's how we figured out everything we know about the universe, from the motion of planets to the expansion of space itself. And it's how we'll figure out 3I Atlas, one spectrum at a time, one calculation at a time, one careful thought at a time. We're about halfway through this documentary now. We've established what we're seeing, nickel emission where it shouldn't be possible. We've explored the physics and chemistry. We've looked at the composition oddities that add context to the central mystery. In the next section, we're going to do something different. We're going to step back from the immediate observations and think about what they mean, not just for our understanding of comets, but for our understanding of the galaxy, of the diversity of star systems, of what else might be out there, wandering between the stars. And yes, we're going to carefully, responsibly, address the technological hypothesis, the question of whether 3I Atlas might be something other than natural. But before we do that, I want to anchor us in wonder, in the sheer strangeness of what we're witnessing. We are primates on a small, rocky planet orbiting an average star in an unremarkable part of a spiral galaxy, and we've developed the technology and the understanding to detect an object from another star system, analyze its chemical composition light minutes away, and recognize that it's made of different stuff than the objects formed around our own star. Think about that. Think about what an achievement that is. Not just technologically, though the telescopes and spectrographs are marvels, but intellectually. We understand atoms. We understand stellar nucleosynthesis. We understand orbital mechanics. We understand chemistry deeply enough to recognize when something is unusual. We've built up this edifice of knowledge over centuries. Newton's laws, spectroscopy, quantum mechanics, nuclear physics, each generation building on the last, each discovery opening new questions. And now we're using that knowledge to decode a message written in vaporized supernova ash, carried across the galaxy for billions of years by a frozen chunk of ice from another sun's family. That's astonishing. That's worth celebrating. The nickel glow we're seeing isn't just interesting scientifically, it's beautiful philosophically. It's evidence that we live in a universe diverse enough to surprise us, complex enough to challenge our models, understandable enough that we can ask questions and get answers, and it's a reminder that we're still learning, still discovering, still finding things that don't fit neatly into our categories. 3i Atlas is one visitor, one object. But it represents countless others we haven't detected yet. Thousands or millions of interstellar objects crossing through our solar system at any given moment, invisible until we get lucky. Each one is a potential teacher. Each one carries information about its birth star, its formation conditions, its billions-year journey. We're just beginning to read these messages. 3 data points, 3 interstellar visitors, a handful of observations. But we're reading them. We're paying attention. We're listening to what the universe is telling us. And what it's telling us, through the green glow of impossible nickel vapor, is that there's still so much we don't know, so much left to discover, so many surprises waiting in the darkness. Let's talk about implications. In October 2025, astrophysicist Avi Loeb, chair of Harvard's astronomy department and founding director of the Black Hole Initiative, published an article about 3i Atlas. The article was measured, careful, and raised a question that many scientists prefer not to discuss publicly. What if 3i Atlas isn't entirely natural? Now, before we go further, let me be absolutely clear about something. Avi Loeb is not a conspiracy theorist. He's not a fringe figure. He's a respected scientist with hundreds of peer-reviewed publications, many in prestigious journals. His work on black holes, the early universe, and the search for extraterrestrial intelligence is serious academic research. But he's also willing to ask questions that make other scientists uncomfortable. Questions about whether some astronomical objects might be artificial, whether we should consider technological explanations alongside natural ones. And with 3i Atlas, he's asking whether the unusual composition, particularly the nickel emission, might be evidence of something designed rather than formed naturally. Let's be honest about what we're discussing here. The claim isn't that 3i Atlas is a spacecraft, not explicitly. The suggestion is more subtle, that the unusual chemical signatures might indicate processing, refinement, intentional concentration of specific elements. Why? The argument goes something like this. If you were building a probe to travel between star systems, you'd want it to be durable, resistant to damage from cosmic rays, micrometeorites, extreme temperature variations. Certain metals, nickel for instance, have properties that make them excellent for such applications. High strength, corrosion resistance, stability across wide temperature ranges. You'd also want your probe to be observable, to emit signals that other civilizations could detect. Maybe you'd design the surface to create distinctive spectral signatures. Maybe the nickel emission we're seeing isn't accidental sublimation, but intentional signaling. Now, here's what's important. This is speculation. Avi Loeb himself acknowledges that the most likely explanation is that 3i Atlas is a natural comet with unusual but explainable composition. He's not claiming we've found an alien probe. He's saying we should consider the possibility and look for evidence that could rule it in or out. That's actually good scientific practice. You don't dismiss possibilities just because they seem unlikely. You examine them, you figure out what evidence would support or refute them, and then you look for that evidence. So let's do that. Let's think about what would distinguish a technological object from a natural one. What would we expect to see if 3i Atlas was artificial? Natural comets are lumpy, irregular, randomly structured. They're accretions of ice and dust, shaped by collisions and gravity but fundamentally disordered. An artificial object would likely show geometric regularity, smooth surfaces, right angles, symmetries that don't occur naturally. Can we test this? In principle, yes. If we could get high-resolution images of 3I Atlas, if it passed close enough for detailed photography, we could look for structural regularity. Unfortunately, 3I Atlas's closest approach to Earth is still 1.8 AU. That's too distant for most imaging systems to resolve fine details. We'll see it as a point source, maybe slightly elongated, but not in enough detail to distinguish geometric structure. So this test is inconclusive. We can't rule out artificiality based on structure because we can't see the structure clearly enough. A manufactured object would likely have compositionally distinct parts. Pure metal here, insulation there, perhaps specific isotopic ratios indicating refined materials rather than natural abundance. Can we test this? Maybe. If 3I Atlas rotates, and if different sides have different compositions, we'd see the spectral lines vary with rotation period. Sometimes more nickel, sometimes less. That would indicate surface heterogeneity. This is actually testable with current observations. Astronomers can monitor the emission over time and look for periodic variations. If they exist, it would suggest distinct surface regions. As of now, I'm not aware of published results showing clear rotational modulation. That doesn't mean it's not there. Analysis takes time, but the absence of obvious periodic variation is mildly against the artificial hypothesis. A natural comet could have heterogeneous composition too, though. Layers of different ice types, inclusions of rocky material. Composition variation is normal. So this test isn't definitive either way. If 3I Atlas were an active probe, we might see trajectory changes that can't be explained by outgassing, course corrections, orbital adjustments, burns that increase or decrease velocity in specific ways. Can we test this? Absolutely. The object's trajectory is being monitored with extreme precision. Any deviation from a purely ballistic orbit, accounting for known outgassing forces, would be detectable and significant. So far, 3I Atlas's trajectory is consistent with a natural object experiencing non-gravitational acceleration from asymmetric outgassing. No evidence of intelligent maneuvering, no unexplained course changes. That's significant. If this were a probe, and if it was still operational, you'd expect some indication of active control. The fact that we're not seeing it argues against the technological hypothesis. An active technological object might emit radio signals, infrared in unusual patterns, or other electromagnetic signatures beyond what natural processes produce. Can we test this? Yes, and it has been tested. Radio telescopes have observed 3I Atlas. The Breakthrough Listen project, specifically designed to search for extraterrestrial technology, has examined it for anomalous signals. Nothing detected. No narrow-band radio emissions, no structured signals, just the thermal and reflected light you'd expect from a comet. Again, this doesn't definitively rule out artificiality. Maybe the probe is defunct, maybe it communicates in ways we're not monitoring, maybe it's deliberately silent. But the absence of signals is evidence, not proof, but evidence, against the technological hypothesis. Here's where we need to apply Occam's razor. The principle that, all else being equal, simpler explanations are more likely to be correct. We have two hypotheses. Hypothesis A, natural. 3. I Atlas is a comet formed in a carbon-rich protoplanetary disk around another, star. It contains unusual but naturally occurring volatile nickel compounds. When heated by sunlight, these compounds sublimate, and UV photodissociation releases free nickel atoms that emit at characteristic wavelengths. Hypothesis B, technological. 3I Atlas is an artificial object, possibly a probe, possibly defunct, designed by an extraterrestrial civilization. The nickel emission is either incidental to its construction materials or deliberately engineered for signaling. Both hypotheses can explain the nickel emission. But hypothesis A requires only known chemistry and known astrophysical processes. Hypothesis B requires the existence of extraterrestrial intelligence, the development of interstellar travel, the motivation to send probes to other star systems, and the coincidence that we're detecting one now. Hypothesis A is simpler. It requires fewer assumptions. Therefore, by Occam's razor, it's the provisional explanation we should favour until evidence forces us to reconsider. Now, Avi Loeb would agree with this reasoning. His argument isn't that we should assume 3I Atlas is artificial. His argument is that we shouldn't dismiss the possibility without investigation. that we should look for evidence that could distinguish between natural and artificial origins, and he's right about that. The problem isn't asking the question. The problem is when people take the question as evidence. When "we should look into this" becomes "this is probably artificial" in public discourse. 3I Atlas is almost certainly a natural comet. The evidence strongly supports that conclusion, but almost certainly isn't definitely, and maintaining scientific rigour means acknowledging uncertainty where it exists. There's precedent for this, actually. When pulsars were first discovered in the 1960s, their incredibly regular timing, millisecond precision pulses seemed impossible for any natural process. The discoverers half-jokingly called the first one LGM-1, Little Green Men 1. Were pulsars artificial? No. They turned out to be rapidly rotating neutron stars, with the pulses generated by magnetic field interactions. A natural phenomenon, just one we hadn't predicted or understood yet. Fast radio bursts, brief, intense pulses of radio waves from distant galaxies, initially seemed mysterious enough that some scientists speculated about artificial origins. Could they be the exhaust plumes of interstellar spacecraft using photon drives? Again, no. They appear to be natural, possibly related to magnetars or neutron star collisions. But the speculation was scientifically reasonable at the time, because we didn't have enough data to rule out exotic explanations. The pattern is consistent. We see something weird, we don't understand it immediately, some people speculate about artificial origins, and eventually we figure out the natural explanation. 3I Atlas will likely follow the same pattern. The nickel emission is weird. We're still figuring it out. Some speculation about artificiality is reasonable, and eventually we'll understand the natural mechanism. But here's what I want you to take away from this section. Asking whether something might be artificial isn't unscientific. What matters is how you ask, what evidence you require, how you update your beliefs as new data arrives. Avi Loeb is asking responsibly. He's not claiming certainty. He's proposing observations that could test the hypothesis. He's maintaining scientific rigour while entertaining an exotic possibility. Others, bloggers, conspiracy theorists, people seeking attention, will take his careful speculation and inflate it into certainty. Scientist says 3I Atlas might be alien probe. Headlines that distort the nuance. That's not Avi Loeb's fault. That's the fault of a media ecosystem that rewards sensationalism over accuracy. As consumers of scientific information, we need to be careful. We need to distinguish between "this is an interesting question worth investigating" and "this is probably true," between speculation and conclusion. So, to summarise, is 3I Atlas artificial? Almost certainly not. The evidence favours a natural origin. The unusual composition can be explained by formation in a different stellar environment. The nickel emission likely results from volatile compounds we haven't encountered in solar system comets, but which are consistent with known chemistry. Should we rule out artificiality completely? No. We should continue to collect data that could test the hypothesis. If we see evidence of active control, geometric structure, electromagnetic signalling, or composition patterns inconsistent with natural processes, we should update our assessment. But absent such evidence, the natural explanation is strongly favoured. There's something else worth considering here, though, something philosophical. The question of artificiality touches on a deeper issue. How rare or common is intelligence in the universe? We don't know. We have one data point: us. We know intelligence can arise. We know technology can develop. We know it's possible to build things that could, in principle, travel between stars. But we don't know if it's common. We don't know if technological civilizations typically survive long enough to send probes to other systems. We don't know if interstellar travel is practical or impossibly difficult. The absence of detected extraterrestrial intelligence, the Fermi paradox, suggests either intelligence is extremely rare, or it doesn't last, or it doesn't expand into the galaxy in obvious ways, or we're not looking correctly. Every interstellar object we detect is, in principle, an opportunity to find evidence. Not because we expect any particular object to be artificial, but because if artificial objects exist, examining interstellar visitors is how we'd find them. So Avi Loeb's suggestion that we should carefully examine 3I Atlas for technological signatures is reasonable even if the probability is low, because the implications if we found something would be profound. It would be the most important discovery in human history. Low probability, high impact. That's a calculation worth making. This is why SETI exists, the search for extraterrestrial intelligence. Not because scientists think most stars have technological civilizations, but because finding even one would change everything, would tell us we're not alone, would prove that intelligence isn't a unique accident, but a replicable outcome of cosmic evolution. 3i Atlas isn't going to be that discovery. The evidence doesn't support it. But examining it carefully, ruling out artificiality with actual observations rather than assumptions, is part of the broader SETI program. And who knows, maybe the 10th interstellar object we detect will show clear signs of artificial origin. Maybe the 100th. Maybe we'll never find one, and that will tell us something important too. That intelligence is rarer than we hoped, or that interstellar travel is impractical, or that civilizations don't survive long enough. Each data point teaches us something. Okay, we've addressed the technological question. We've done it seriously, carefully, without dismissing it or inflating it. We've applied scientific reasoning and concluded that 3i Atlas is most likely natural. Now let's talk about what the natural explanation teaches us, because even if this is just a comet, it's a comet with a story to tell. A story about ancient star systems, about chemical diversity, about the processes that make worlds. 3i Atlas is old. Potentially very old. Preliminary estimates based on its trajectory and the dynamics of galactic orbits suggest it could be anywhere from 3 billion to 11 billion years old. Let me give you perspective on those timescales. Our solar system, Sun, Earth, everything we've ever known, is 4.6 billion years old. If 3i Atlas is 11 billion years old, it predates our entire existence by 6.5 billion years. The universe itself is only 13.8 billion years old. If 3i Atlas formed 11 billion years ago, it formed when the universe was only 20% of its current age, when galaxy formation was still in its early stages, when the first generation of stars was still young. Think about what the galaxy looked like then. Fewer heavy elements, less carbon, oxygen, iron, nickel, because fewer generations of stars had lived and died and enriched the interstellar medium with supernova debris. The star around which 3i Atlas formed was probably a second or third generation star, formed from gas clouds that had been enriched by 1 or 2 rounds of supernovae, but still metal poor compared to our Sun, which formed much later and benefited from billions of additional years of cosmic chemical evolution. In astronomy, metal means anything heavier than helium. So carbon is a metal, oxygen is a metal, iron, nickel, gold, all metals. The abundance of these elements in a star or gas cloud is called its metallicity. Young, early universe stars have low metallicity. Later stars have higher metallicity. Our Sun is classified as a population 1 star, high metallicity, formed in a relatively metal-rich environment. If 3i Atlas is 11 billion years old, it formed around a star with much lower metallicity than our Sun, less carbon, less oxygen, less of everything except hydrogen and helium, and yet, somehow, it incorporated enough heavy elements to show distinct chemical signatures, enough carbon dioxide to dominate its volatile composition, enough nickel to emit strongly when sublimating. That tells us something interesting. Even in the early universe, even in metal-poor environments, planet formation was happening. Comets were forming, and they were incorporating heavy elements, the products of supernovae, into their ice. Picture the scene. A young star, perhaps a K-type, cooler and redder than our Sun, surrounded by a disk of gas and dust. The disk is mostly hydrogen and helium, but it's been enriched slightly by a nearby supernova. Wisps of carbon, oxygen, silicon, iron, nickel, supernova ash, mixing into the primordial gas. The disk cools, molecules form, carbon monoxide, water, silicon monoxide. In the coldest regions, these molecules condense into ice grains, tiny particles, micrometers across, drifting in the disk. The grains stick together when they collide. Electrostatic forces, molecular adhesion, the same physics that makes snowflakes clump, cause the grains to agglomerate. Millimeter-sized clumps, centimeter-sized, meter-sized. Over millions of years, these grow into kilometre-scale objects, comets, asteroids, the building blocks of planets. Some of these objects remain in the outer disk in stable orbits for billions of years. Others get ejected, flung out by gravitational interactions with forming planets, or close passes with the star, or perturbations from nearby stellar systems. One of these ejected objects is 3I Atlas. It left its birth system carrying a sample of the disk's chemistry: CO2-rich ice, nickel compounds, organic molecules, a frozen record of conditions in a protoplanetary disk that existed when the universe was young, and then it wandered, for billions of years, through the galaxy, past other stars, close enough to feel their gravity but not close enough to be captured, through the spiral arms, through regions of active star formation where supernovae were enriching the medium, through quiet voids between stars where nothing happened for millions of years. It travelled perhaps thousands of light years, maybe tens of thousands. The galaxy rotates, stars move in their orbits, and over billions of years even nearby stars drift apart. The star where 3I Atlas formed could be anywhere now, on the other side of the galaxy or in a completely different part of the spiral arm. We'll never know which star it was. We can backtrack 3I Atlas's trajectory, project it backward through space, but the uncertainties accumulate. After a few million years, the error bars are larger than the distances between stars. After a billion years, we've lost the trail completely. The origin star is unknowable, but the chemistry remains, frozen in ice, preserved by the cold of interstellar space. Although preserved isn't quite accurate. 3I Atlas has been bombarded by cosmic rays, high-energy particles zipping through this galaxy for its entire journey. Those impacts leave marks. They damage molecular structures. They create radiation tracks in ice. They alter isotopic ratios through spallation reactions. These effects are measurable. If we could collect a sample, if we could land on 3I Atlas and bring material back to a laboratory, we could measure the cosmic ray exposure age. How long the material has been exposed to space. That would give us a direct measurement of how long this object has been wandering. We can't do that, unfortunately. 3I Atlas is moving too, fast, and will be gone in months. No spacecraft we have could catch it. The opportunity for sample return doesn't exist, but future interstellar visitors? Maybe. If we detect one early enough, if it's moving slowly enough, if we can launch an intercept mission, someday we might bring back samples from an interstellar comet, and the isotopic analysis of that sample would teach us things we can't learn any other way. For now, we're limited to remote observation, spectroscopy, photometry, astrometry. We can analyse the light, measure the trajectory, infer the composition from emission and absorption lines. And what we're inferring is fascinating. This isn't just a comet with unusual composition. This is potentially a window into chemistry that doesn't exist in our solar system. Chemistry from a different stellar environment, from a different epoch of galactic history. The CO2 dominance? That might be characteristic of comets formed in carbon-rich disks, which could be more common around certain types of stars. The nickel emission? That might tell us about metal abundance and speciation in those ancient disks. Every piece of data is a clue, not just about this one object, but about the diversity of outcomes in planet formation, about how different stellar environments produce different kinds of objects. Our solar system formed around a G-type star, yellow, medium temperature, relatively high metallicity, and it produced a certain distribution of objects. Rocky planets close in, gas giants farther out, icy bodies in the outer system, comets and asteroids with characteristic compositions. But most stars in the galaxy aren't G-type. Most are smaller, cooler M-type stars, red dwarfs. Their planetary systems probably look different. Different snow lines, different planet sizes, different comet compositions. There are also hotter stars, A-type and F-type, bluer, more luminous. Their snow lines are farther out, their radiation fields are different. The chemistry in their disks might favour different molecules. And then there are the rare stars, carbon stars, which produce more carbon than oxygen in their fusion processes. Their planetary disks would be carbon-rich, silicon carbide grains instead of silicate dust, carbon-based ices instead of water-dominated ices. Could 3I Atlas have formed around a carbon star? It's possible. The CO2 dominance, the potential for nickel carbonyl, these are consistent with a carbon-rich formation environment. We don't know, but we're learning. Each interstellar visitor teaches us about the range of possibilities. There's something poignant about this, isn't there? 3I Atlas has been travelling for billions of years, through the darkness, through the empty spaces between stars, frozen, silent, carrying its chemical memories, and then, by pure chance, it enters our solar system, gets close enough to our sun to warm slightly, begins to outgas, starts glowing green with vaporized nickel, and we notice. We point our telescopes at it. We analyze its light. We puzzle over its composition. We write papers and build models and make documentaries. For a few months, this ancient traveller has our attention. We're trying to understand it, to read the story written in its chemistry. And then it will leave. It will accelerate past the outer planets, beyond the heliopause, back into interstellar space. The sun's warmth will fade, the outgassing will stop, the nickel emission will cease, and 3i Atlas will resume its journey, silent again, frozen again, travelling through the galaxy toward another encounter that might happen in 1,000,000 years, or 10 million, or never. And 3i Atlas will resume its journey, silent again, frozen again, travelling through the galaxy toward another encounter that might happen in 1,000,000 years, or 10 million, or never. Where is it going? We can calculate that, actually. Its trajectory is hyperbolic, but the direction is measurable. When it leaves our solar system, it will be heading roughly toward the constellation Aries, not toward any particular star. The distances are too vast, the journey too long, but in that general direction. In 50,000 years, it will be a light year away. In 1,000,000 years, 20 light years. In 10 million years, 200 light years. Will it encounter another star? Probably, eventually. The galaxy is vast but not infinite. Over billions of years, close passes are likely. Maybe it will be captured into orbit around another star. Maybe it will be destroyed in a collision. Maybe it will simply continue wandering. We'll never know. This brief encounter, this window of a few months when 3i Atlas is close enough for detailed study, is the only time humans will ever interact with this object. That's true of all the interstellar visitors we detect. They're not coming back, they're not staying, they're passing through, giving us one chance to learn what we can. 3 objects so far: Oumuamua, Borisov, 3i Atlas, 3 messengers from other star systems, 3 samples of the diversity of objects wandering the galaxy. And we're just beginning to detect them. Our survey telescopes are getting better, our detection algorithms are improving. The Vera Rubin Observatory, when it comes online, will detect dozens or hundreds of interstellar objects, maybe thousands. Each one will teach us something. Each one is a free sample returned from a stellar environment we can't visit. Each one expands our understanding of what's possible. The nickel emission from 3i Atlas might turn out to be rare, or it might be common in certain types of comets, and we just hadn't seen it before. We'll only know when we detect more objects and compare them, and maybe, we'll eventually be able to do more than observe. Maybe we'll develop the technology to intercept an interstellar visitor, to match velocity with it, to study it up close, to land on it and collect samples. That's not science fiction, it's engineering. Difficult engineering, but possible with enough resources and motivation. The ESA is already planning a mission called Comet Interceptor, designed to reach a long-period comet or possibly an interstellar object if one is detected early enough. It won't launch for years, and it won't catch 3i Atlas, but it's a start. Proof that we're thinking about these problems. Imagine what we could learn from a sample return mission. Imagine bringing back a gram of material from 3i Atlas. The isotopic analysis, the organic molecule inventory, the crystalline structure of the ice, the cosmic ray exposure age. Every question we're puzzling over. Now, the nickel composition, the formation environment, the age, could be answered definitively with laboratory analysis. That's the future. Not this decade, probably not next decade, but eventually. We'll get there. But even without sample return, even with just remote observation, we're learning profound things. We're discovering that the galaxy is more chemically diverse than we realized, that comet formation isn't uniform, that star systems produce different outcomes depending on their conditions. 3i Atlas is teaching us that comet is a category with wide variation. Solar system comets are one type. Borisov represents comets similar to ours from other systems. 3i Atlas represents something else. Comets from carbon-rich or metal-enriched environments. And there are probably other types we haven't seen yet. Each type tells a story about stellar metallicity, about protoplanetary disk chemistry, about the temperatures and pressures and elemental abundances in the region where it formed. We're cosmic archaeologists. We're studying artifacts from ancient stellar civilizations, not technological civilizations, but stellar ones. The the communities of stars that were forming planets when the universe was young, and the artifacts are teaching us their history. The green glow of nickel vapor is more than just a scientific curiosity. It's a signal, a message from the past, from a star that died or dispersed billions of years ago, from a disk of gas and dust that doesn't exist anymore, from conditions we can study only through the frozen samples that escaped. And we're reading that message, decoding it, understanding it. That's what science is, at its heart. Reading the messages the universe sends us, interpreting the evidence, building models that explain what we see and predict what we'll find next. 3i Atlas sent us a message written in vaporized supernova ash, in carbon dioxide ice, in organic molecules and isotopic ratios and emission line intensities, and we're reading it, word by word, spectrum by spectrum, thought by thought. That's beautiful. That's what makes this work meaningful. Not just the discovery itself, but the process of discovery, the careful observation, the patient analysis, the collaboration between minds separated by continents but united by curiosity. We're going to shift now. We've covered the science, we've addressed the technological speculation, we've explored what the ancient chemistry teaches us. In the final act, we're going to get philosophical. We're going to ask what all of this means. Not scientifically, we've covered that, but existentially. What does it mean to witness an interstellar visitor? What does it tell us about our place in the universe? About the nature of discovery and knowledge and wonder? And we're going to talk about endings, because 3i Atlas is leaving. In a few months it will be gone, and we'll never see it again. How do we hold that? How do we process the transience of this? Encounter? That's what the final act is about. Meaning and farewell. But before we get there, let me tell you one more thing about the nickel. One more layer to the mystery that I haven't mentioned yet. The nickel emission isn't constant. It varies. Not dramatically, but measurably. Some nights it's stronger, some nights it's weaker, and there might be a pattern to the variation. If the pattern is real, if it correlates with 3i Atlas's rotation period, it would tell us that the nickel source isn't uniformly distributed across the surface, that there are regions richer in nickel compounds, maybe specific vents or cracks where outgassing is concentrated. That would be fascinating. It would tell us about the internal structure, about how the composition varies with location, about whether there are distinct ice layers or chaotic mixing. The data analysis is ongoing. By the time you watch this documentary, we might have answers, or we might have more questions. Either way, it's another example of how rich these observations are, how much there is to learn from careful, patient study. The universe rewards attention. If you look carefully enough, if you measure precisely enough, there are always more layers, more details, more subtleties to discover, and 3i Atlas is full of subtleties. Let's talk about what it all means. Here is Earth, our home, a rocky planet 8,000 miles in diameter, orbiting a yellow star in the outer regions of a spiral galaxy. On this planet, approximately 3.7 billion years ago, something remarkable happened. Chemistry became biology. Non-living matter organized itself into patterns that could reproduce, evolve, and eventually think. Over billions of years, through countless iterations and extinctions and evolutionary innovations, that biology produced us, humans, primates with oversized brains and opposable thumbs, and an apparently insatiable curiosity about how things work. And now, in the year 2025, some of those humans are pointing telescopes at a green light in the sky and analysing its spectrum. They're measuring the wavelength of photons that travelled millions of miles from a frozen chunk of ice. They're identifying specific atoms, nickel, based on the precise energy levels of electron transitions. Think about what an unlikely chain of events that represents. What an extraordinary outcome. The universe begins, hydrogen and helium form, the first stars ignite. They forge heavier elements and explode. The debris mixes, new stars form from enriched material. Planets accrete. Life begins. Evolution proceeds. Intelligence emerges. Technology develops. And at the end of that 13.8 billion year process, consciousness exists. Awareness exists. We exist. Able to look outward and understand, at least partially, what we're looking at. We can observe a comet from another star system and recognize it as such. We can infer its composition, its trajectory, its age. We can wonder about its origins and hypothesize about its chemistry. That's astonishing. That's miraculous in the non-religious sense of the word. It's deeply, profoundly unlikely that the universe would produce anything capable of understanding the universe. And yet here we are. 3i Atlas doesn't know we're watching it. It can't. It's not conscious. It's just matter, ice and rock and frozen gases, following the laws of physics. It doesn't care that it's unusual. It doesn't care that it's vaporizing nickel in ways that confuse our models. It's simply being what it is. But we care, we notice, we wonder, we try to understand. And in doing so, we're fulfilling a role that, as far as we know, is unique in the universe. We're the part of the universe that looks at itself, the part that asks questions, the part that builds models and tests them and refines them. Carl Sagan said it beautifully. We are a way for the cosmos to know itself. 3i Atlas is part of the cosmos, so are we. And when we study 3i Atlas, when we decode the messages written in its chemistry, we're engaging in cosmic self-reflection. The universe examining itself. Matter understanding matter. Now, I want to be careful here. This isn't mysticism. This isn't claiming there's some deeper purpose or meaning baked into reality. The universe isn't conscious. It doesn't have intentions. But we are conscious. We do have intentions. And one of those intentions is to understand, to figure out how things work, to ask why. And that intention, that curiosity, is itself a natural phenomenon. It evolved because it was useful. Organisms that understood their environment survived better than organisms that didn't. Curiosity about how things work translated into better tools, better strategies, better survival outcomes. So in a very real sense, our drive to understand 3i Atlas is the same drive that helped our ancestors survive on the African savanna. The same impulse that made them curious about which plants were edible and which animals were dangerous. Except now we're applying that impulse to questions that have no survival value. Understanding comet chemistry doesn't help us find food or avoid predators. Analysing nickel emission doesn't improve our reproductive success. We do it because we're curious, because we want to know, because the question is there and we can't help but try to answer it. This has always been true. Humans have always looked up. Ancient cultures mapped the stars, tracked the planets, wondered about the cosmos. They didn't have our tools or our knowledge, but they had the same curiosity. They couldn't know that the stars were distant suns. They couldn't know about nuclear fusion or spectroscopy or interstellar objects. But they looked up, they wondered, they tried to understand, and over generations, over centuries, that wondering accumulated into knowledge, astronomy, physics, chemistry. The scientific method itself, this process of careful observation and hypothesis testing and gradual refinement of understanding, we're standing on the shoulders of thousands of years of accumulated wondering. Every person who looked up and asked, "What is that?" Every person who made a careful observation and wrote it down. Every person who tested an idea and found it wanting and tried again. All of that history, all of that accumulated knowledge has brought us to this moment, where we can look at a green light in the sky and say with certainty, that is nickel vapor from a comet formed around another star, vaporizing at temperatures that shouldn't allow it. We know so much. The periodic table of elements, quantum mechanics, spectroscopy, orbital dynamics, stellar nucleosynthesis, the Big Bang, galaxy formation, planet formation, the chemistry of comets. Every one of those topics represents decades or centuries of work. Thousands of scientists, each contributing a piece, each expanding our understanding slightly, and all of that knowledge is accessible to you. Not just to professional astronomers, to anyone willing to learn. The books exist, the papers are published, the data is often freely available. This documentary is part of that tradition. It's taking the specialized knowledge of astronomers and spectroscopists and making it understandable to a general audience, translating the technical details into narrative, explaining the context, sharing the wonder. Because the wonder is worth sharing. The strangeness of impossible nickel vapor, the beauty of spectroscopy, the profound timescales of cosmic wandering, the philosophical implications of consciousness studying the universe. These aren't just facts, they're part of the human story, part of what makes our species remarkable, and maybe, some person watching this will be inspired. Will decide to study astronomy, or chemistry, or physics. Will contribute to the next generation of understanding. Will help us decode the next interstellar visitor, or solve some other cosmic mystery. That's how knowledge grows. Not through individual genius alone, but through accumulation, through teaching, through inspiration cascading from one generation to the next. Every great scientist was inspired by someone, every breakthrough built on previous work, every discovery opened new questions that drove further discovery. 3i Atlas is part of that chain. It's raising questions, challenging our models, forcing us to think more carefully about comet composition and volatile chemistry and stellar environments. And the answers we develop, even if they're not perfect, even if they're refined or overturned later, will contribute to the next step. They'll inform how we think about the next interstellar visitor. They'll expand the space of possibilities we consider. Let me tell you why I think this matters personally, not scientifically. We've covered that, but why I care, why I'm making this documentary series, why I think you should care too. We live in a strange time, a time of rapid change and global challenges and often overwhelming complexity. It's easy to feel small, to feel like individual actions don't matter, to feel disconnected from anything larger than immediate personal concerns. But when I think about 3i Atlas, when I really sit with what it represents, I feel connected. Not in a mystical sense, but in a tangible one. That nickel vapor came from a supernova. The atoms were forged in the nuclear fires of a dying star. They travelled through space, mixed into a molecular cloud, condensed into a comet, wandered for billions of years, and ended up close enough to our sun that we could detect their emission. And I'm made of the same stuff. Carbon from an ancient supernova, oxygen from stellar fusion, iron in my blood, nickel in trace amounts throughout my body. All of it came from stars that died before the sun was born. I'm not separate from this story. I'm part of it. We all are. We're made of star stuff, as Carl Sagan said. We're the universe examining itself. Every atom in your body was once somewhere else. In a star, in a nebula, in a protoplanetary disk, in the early Earth, in ancient oceans, in organisms that lived millions of years ago. The atom cycle. They move from one form to another. They're borrowed temporarily, assembled into the pattern that is you, and will eventually return to the cycle. Right now, you're a pattern of atoms that can think, that can wonder about interstellar comets and nickel emission, that can appreciate the strangeness and beauty of the universe. That pattern won't last forever. Nothing does. But right now, in this moment, it exists. You exist. You're conscious. You're aware. You can choose to pay attention to things like 3i Atlas or not. And I think there's meaning in choosing to pay attention, in choosing to learn, in choosing to wonder. Because 3i Atlas won't be here long. A few more months of observation, and it will be gone, beyond the range of our telescopes, accelerating into the darkness, resuming its billion-year journey through the galaxy. We'll never see it again. No human ever will. This is the only encounter, the only chance. And that's true of everything, really. Every moment is unique. Every experience happens once. You can't step in the same river twice, as Heraclitus said, because both you and the river have changed. 3i Atlas makes that truth visceral, makes it cosmic. Here is an object that has been travelling for billions of years, and by pure chance it passed close enough to our sun that we could see it, for a few months, and then it's gone forever. How do you hold that? How do you process the transience? I think you hold it by paying attention, by really being present for it, by not taking it for granted. Every spectrum we collect matters. Every observation matters, because we won't get another chance. This is it. The window is closing, and in a way, that makes it more precious. If 3i Atlas were going to orbit the sun for centuries, we could study it leisurely. We could put off observations, knowing we could always return later. But we can't. The deadline is real. January 2026, it will be too far away. The observations will end, the data collection will stop, and then we'll have what we have. A collection of spectra, photometric measurements, trajectory calculations, models and papers and discussions, that's all. And from that collection of data, we'll try to understand, we'll build the best models we can. We'll draw conclusions, always provisional, always subject to revision if better data becomes available. But the data won't get better. 3i Atlas is leaving. What we collect now is what we'll have to work with for the rest of human history. Unless, and here's a beautiful thought, unless we detect another similar object someday. Another CO2-dominated interstellar comet with nickel emission. A chance to test whether what we're seeing in 3i Atlas is unique or representative. That's the hope. That 3i Atlas is the first of a type, not a singular anomaly. that we'll detect more objects with similar chemistry and gradually understand the conditions that produce them. Each interstellar visitor adds to our knowledge. Oumuamua taught us that interstellar objects can be strange and hard to categorize. Borisov taught us that some are reassuringly normal. 3i Atlas is teaching us about chemical diversity and the limits of our models. And the next one, who knows? Maybe it will clarify things. Maybe it will deepen the mystery. Either way, we'll learn. The Vera Rubin Observatory will come online in the next few years. It will survey the entire visible sky every few nights, detecting transients and moving objects with unprecedented efficiency. It will find dozens of interstellar visitors, maybe hundreds over its operational lifetime. Each one will be a sample, a data point, a messenger from another stellar environment, and collectively they'll teach us about the diversity of planet formation in our galaxy, about which types of chemistry are common and which are rare, about the conditions in different stellar environments. 3i Atlas is the beginning of that catalogue. The third entry. Each entry teaches us something, and collectively they'll teach us far more than any individual object could. But right now, tonight, 3i Atlas is here, glowing green with impossible nickel vapour, moving through our outer solar system at 62 kilometers per second, observable, measurable, real, and you know about it. You've spent 2 hours learning about it, understanding what makes it strange, appreciating the science and the mystery and the meaning. That matters. Not in a cosmic sense. The universe doesn't care whether you know about 3i Atlas or not, but in a human sense, in the sense that knowledge and wonder and curiosity are valuable. You're more aware of the universe now than you were 2 hours ago. You understand something about spectroscopy and sublimation and chemical composition. You've thought about deep time and ancient stars and the transients of encounters. That's not nothing. That's growth. That's expansion of consciousness. And maybe you'll share what you've learned. Maybe you'll tell someone else about the green comet with impossible nickel vapour. Maybe they'll be intrigued and look into it further. Knowledge spreads like that, person to person, mind to mind. Each transmission slightly different, each person emphasizing different aspects, but collectively building a culture that values understanding. We need that culture, especially now. In a time when misinformation spreads easily and critical thinking is undervalued, we need people who care about evidence, who want to understand how things actually work, who can distinguish between speculation and conclusion. 3i Atlas is a perfect example of how science should work. We observe something unusual, we measure it carefully, we develop hypotheses to explain it. We test those hypotheses with continued observation. We update our understanding as new data arrives. We don't jump to conclusions, we don't cling to explanations that don't fit the evidence. We don't dismiss possibilities prematurely. We stay curious. We stay humble. We accept that the universe is complex and strange, and that our understanding is always incomplete. That's the scientific mindset, and it's valuable far beyond astronomy. It's a way of thinking that applies to everything. To medicine and engineering and policy and personal relationships. Evidence matters. Testing matters. Being willing to be wrong matters. 3i Atlas will leave. We'll watch it fade. The telescopes will track it as long as they can, squeezing every last photon of data from its receding light. And then it will be gone, beyond detection, accelerating into the darkness between stars. It won't know we watched it, won't know that for a brief time it was the focus of human attention and wonder, won't carry any memory of passing through our solar system. But we'll remember. The data will exist, the papers will be published, the models will be refined, and someday, maybe decades from now, someone will read about 3i Atlas and be intrigued. They'll pull up the archived spectra. They'll see that green nickel line at 5,867 angstroms and wonder, as we wonder now, how it could be vaporizing so far from the sun. And maybe by then we'll know. Maybe we'll have detected enough similar objects to understand the mechanism. Maybe we'll have sampled an interstellar comet and confirmed the volatile compound hypothesis. Maybe the mystery will be solved, or maybe it won't. Maybe 3i Atlas will remain an outlier, a single strange observation that doesn't quite fit the models, a reminder that the universe is under no obligation to make sense to us. Either way, it will have served its purpose. It will have taught us something, even if that something is just, we don't understand everything yet. I want to leave you with one last idea, One last way to think about what 3i Atlas represents. We are ephemeral. Humans live decades, maybe a century if we're lucky. Civilizations last millennia. Even the longest-lived human structures, the pyramids, ancient monuments, will erode given enough time. But the universe endures. Stars burn for billions of years. Galaxies persist across cosmic ages. And objects like 3i Atlas, these frozen wanderers, can travel for billions of years, carrying their chemical messages across unimaginable distances. In a very real sense, 3i Atlas is more permanent than we are. It will outlast our civilization. It will outlast our species, probably. It will still be travelling through the galaxy long after the sun has died and Earth is gone. And yet, right now, for this brief moment, we're the ones with consciousness. We're the ones asking questions and building models and trying to understand. The universe is vast and old and will continue long after we're gone. But right now, we're the part that's awake. That's paying attention. That cares. So, here we are, on a small planet orbiting an average star in an unremarkable part of the galaxy. And we're looking up. We're noticing a green light. We're analysing its spectrum. We're wondering what it means. That's extraordinary. That's beautiful. That's worth celebrating. 3i Atlas is teaching us about chemistry and formation conditions and the diversity of stellar environments. But more than that, it's reminding us of what's possible, that the universe is strange and surprising, that there's always more to learn, that wonder is still available to us if we choose to pay attention. Thank you for watching. Thank you for caring. Thank you for spending 2 hours wondering about nickel vapor and ancient chemistry and the meaning of transient encounters. Go outside tonight if you can. Look up. You probably won't see 3i Atlas with the naked eye. It's too faint. But it's there, somewhere in the darkness, glowing green with impossible nickel vapor. And now you know why that matters.